start the recording, and then let's do another one with finding whether eigenvalues are defective or not. Next up, where's my next example? Hold, please. Let's do this one. For example, A is equal to, I'm reading across, -2, -9, 0, 1, 4, 0, 1, 3, 1. So once again, I'm giving you some zeros to help you out. -2, -9, 0, 1, 4, 0, 1, 3, 1. First up, eigenvalues. So 0 equals the determinant of lambda I minus A. That's going to be the determinant of, careful, lambda plus 2, right? Lambda plus 2, 9, 0, -1, lambda minus 4, 0, -1, -3, lambda minus 1. Okay, I am going to skip the algebra. This example is in my notes. I'll trust that you can write out the determinant, do the algebra, and this ends up being lambda minus 1 quantity cubed. Okay, lambda minus 1 quantity cubed. I'm going to assume that you can multiply out and factor and that you can do the algebra lambda minus 1 quantity cubed. So therefore my eigenvalues are lambda equals 1, 1, and 1. Same eigenvalue 3 times. So my algebraic multiplicity, which I'm going to start abbreviating, is equal to 3. Algebraic multiplicity is equal to 3 in this case. All good? So far, so good? Algebraic multiplicity equals 3. All right, let's look for free variables. So here's my matrix. If I plug in 1, 3, 9, 0, -1, -3, 0, -1, -3, 0. Okay. The entries that I need to zero out are the -1, the -1, and the -3. Those are my entries that I need to zero out in the bottom. So we can do 1/3 row 1 plus row 2 get sent to row 2, and 1/3 row 1 plus row 3 get sent to row 3. It'll let me zero stuff out. And if I do that, I end up with 3, 9, 0, 0, 0, 0, 0, 0, 0. Once again, my columns get labeled V1, V2, V3, right? That's what I'm trying to find. That's my labeling of my columns. So leading non-zero entries are just the 3. There are no other rows that have a first entry, which is non-zero. Therefore, my leading variables, or variable in this case, is V1. And my free variables are V2 and V3. So leading variable is V1, free variables are V2 and V3, and therefore this is an eigenvalue that is defective. And what we would say is that defective with defect, 3 minus 2 equals 1. Your defect is the algebraic multiplicity minus the number of free variables. So that's how you figure out your defect. The algebraic multiplicity minus the number of free variables. That's your defect. So this one is defective with defect 1. That's the sad case, and we will talk about that tomorrow, how to deal with the sad case. Are we good? Everybody good up till now? Okay, leading variables, free variables, defective, not. Yes? Happy? Okay, so now that we've got a way to tell whether we have defective or not, let's go talk about non-defective eigenvalues. So non-defective eigenvalues. Remember, this is the happy case. We like this case. So what we can do is for an eigenvalue with algebraic multiplicity equal to k, we need to find k linearly independent eigenvectors. If we can do that, we'll be back to where we were. And then we can put them back together with the v and the e to the lambda t and multiplying them and adding them and putting them with coefficients. So let's go back to what we had before, my original example with my matrix A. Let me copy it down again since I don't have my chalkboard up and I don't have any chalk and I'm tired of writing on a whiteboard, but here we go. So A was 2, 0, 0, negative 7, 9, 7, 0, 0, 2. And then my lambda I minus A, because I'm going to need that when I plug stuff in. Lambda I minus A was lambda minus 2, 0, 0, 7, lambda minus 9, negative 7, 0, 0, lambda minus 2. And again, remember my eigenvalues were lambda equals 2, 2, and 9. Okay, so we've done this for lambda equals 2, a bunch of it. We got to, I'm skipping steps, 7, negative 7, negative 7, 0, 0, 0, 0, 0, 0. We got there, right? Back to the previous example. Now that I have my negatives in the right spot, 7, negative 7, negative 7, and then a whole bunch of zeros left at the end. And again, remember these are V1, V2, and V3. So we said our free variables were V2 and V3. And here's the equation that I have. This should look familiar from last time. 7V1 minus 7V2 minus 7V3 equals 0, right? 7V1 minus 7V2 minus 7V3 equals 0. Remember, technically this is an augmented matrix, but the part on the right side, the augmented part, is all zeros, so I'm not bothering to write it down. Here's the reason that we're calling these things free variables. The reason that we're calling these things free variables is we can pick them. So I need 2 linearly independent eigenvectors associated with lambda equals 2. Yes, the algebraic multiplicity is 2. I need 2 linearly independent eigenvectors. So my choice is going to be for eigenvector number 1. We chose stuff last time. We're doing the same thing here. We can choose our free variables. So choose V2 equals 1 and V3 equals 0. You can choose anything you want. We chose anything we wanted last time. You can choose anything you want this time. I'm going to choose V2 equals 1 and V3 equals 0. And then V1, if you solve in your equation here, can we do this with fingers? We can do this with fingers. Solve for V1. What is V1 going to have to be in your equation? If you solve and do this with fingers, V1 is going to have to be 1. Yes, good. Okay, so eigenvector number 1, my vector V is 1, 1, 0, going in order, right? V is 1, 1, 0. We'll call this V1. And therefore, X1 is e to the 2t times 1, 1, 0, right? That was how I got my X1 last time. E to the 2t times 1, 1, 0. Everybody good? Nod at me, give me a thumbs up, tell me we're doing okay. Good, all right. Eigenvector number 2. So for eigenvector number 2, I can also make a choice. And this time I'm gonna choose x2 to equal 0 and those are V's, V2 to equal 0 and V3 to equal 1. So we're gonna choose V2 to equal 0 and V3 to equal 1. You can make whatever choice you want. There is no wrong answer here. You just need to be careful that you don't have choices being multiples of each other. So a good way to do that is to pick one of the free variables to equal 1 and the rest to equal 0, and then just kind of cycle through. if I do that, what's V1 gonna have to be? Again, we can do this with fingers. Hold up fingers for me. V1 is gonna have to equal fingers, fingers. Now people are having less interest in fingers. 1, thank you, 1. V3 is gonna have to equal 1. So my vector V2 is 1, 0, 1. Putting those in order, right? V2 is 1, 0, 1. And therefore my vector X2 is e to the 2t times 1, 0, 1.
Would that be vector x2, or should the x1 also be vector x1?
X1 should also be a vector. So this is vector x1. Thank you. Vector x1 and vector x2. Thank you. I forgot to put my vector arrow on x1. It was written in bold. You can't see that? Okay, so we've got 2 linearly independent eigenvectors in this case. We have to come up with another one. And luckily, we have another eigenvalue that we haven't used yet. So we're going to go with lambda equals 9 and repeat this process. So, new slide, because these problems take a while. For lambda equals 9, here's what I get. I am going to get 7, 0, 0, 7, 0, negative 7, 0, 0, 7. That's plugging into lambda I minus a. 7, 0, 0, 7, 0, negative 7, 0, 0, 7. We're seeing that. We're seeing where that comes from. Nod at me. Give me a thumbs up. Tell me we're seeing where that comes from. Okay, got to zero out some things here. So here's what I'm looking to zero out. Negative row 1 plus row 2 can get sent to row 2. Negative row 1 plus row 2 can get sent to row 2. And if I do that, I am going to get 7, 0, 0, 0, 0, negative 7, 0, 0, 7. Okay, so I've zeroed out everything I need to. We can do V1, V2, and V3. We can write down our equations here, right? Let's identify leading variables and free variables just for the fun of it, because this one's a little bit different than we've seen before. So my leading variables, this first 7 goes with V1. So V1 is going to be a leading variable. The negative 7 goes with V3, right? So V3 is going to be a leading variable. And the positive 7 also goes with V3. So I don't have to write it down twice. And therefore, my free variable is V2. So if I put this in terms of equations, we're going to have 7V1 equals 0, negative 7V3 equals 0, and 7V3 equals 0. First line, negative or positive 7V1 equals 0, negative 7V3 equals 0, and 7V3 equals 0. And this is where it's helpful to list leading and free variables, because the free variables are the ones that I get to choose. So we're going to choose V2 equals anything you want. I'm going to channel Daniel and make V2 equal to pi, just because I can, just because we can. Why not? We'll write down pi. It doesn't affect the rest of it. And then I have to have V1 equals 0 and V3 equals 0. Yes, coming from those equations. All right, so my vector V3, we're up to V3 in this case. My vector V3 is 0, pi, 0. And my vector X3 is e to the 9t times 0, pi, 0. You could have picked 1 if you wanted to, but that's boring. And it doesn't affect anything else. It doesn't make the algebra all that much more difficult. All right, so let's go general solution. Here's my general solution. I am going to have vector x equals c1 vector x1 plus c2 vector x2 plus c3 vector x3. That's my general solution when I put all of this back together. Or I can do function x1 of t, function x2 of t, function x3 of t. I think I'm going to get this right, but catch me if I'm wrong because I'm going off of memory from the previous slide. C1 e to the 2t plus, no, I can't do it off of memory. Sorry. C1 e to the 2t plus C2 e to the 2t plus 0. There's no plus in this one because my top entry up here is equal to 0. So no plus, just a 0. That's a C2 and an E. X2 is going to be C1. Nope. This is just not working. I can't visualize it. C1 and a 0. C1 e to the 2t, that next part is 0, plus pi C3 e to the 9t, right? That's my third part there. And then my last one, if I bounce back one more time, is going to be C2 e to the 2t. I think that's right. Are we okay with that? I'm bouncing back and forth between two slides and it's causing me a little bit of confusion. Yes, we're happy. People are nodding at me. Okay. All right. So if you have non-defective eigenvalues, the process is basically the same. The only thing that changes is your chooses. So you're going to have to go through multiple chooses, and that's where identifying your free variables is really, 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 really helpful because those are your chooses in this case. One thing we didn't do, and we would again for the 850th time, prove this if we were in linear algebra. We did not prove that x1, x2, and x3 were linearly independent. We could, we didn't. If it were linear algebra, we would, and we could prove that using the Wronskian. So you could go ahead and put the Wronskian together of those three and make sure that we get vectors that are linearly independent. All right, I'm going to stop sharing my screen. Questions? That was a lot, and it's a lot of heavy process, but hopefully the steps make sense. Questions to this point? What do we got? Bethany, yes.
So if it shows up in like homework or the test, do we have to prove that they're linearly independent or not?
Only if I specifically ask you to. So I'll be very clear about asking you to show linearly independent or not. If I don't ask for it, you can assume that you have linearly independent eigenvectors. Good question. Other questions? Abby, yeah.
So when we were doing like the different matrix stuff with ours, so I didn't like take linear algebra, so I still don't like quite understand all the properties that you can do, but for one of them you just switched them, you just flipped them.
Yep.
So are there like any other special ones, or are you gonna put like really hard ones on the test?
No, so those are, remember we talked about those three properties you're allowed to do. This was a couple of days ago. You can interchange two rows. You can multiply a row by a non-zero scalar constant, and you can multiply a row by a non-zero constant and add it to another row.
Okay.
Those are the ones you're allowed to use. So
Okay.
I promise to not make them super hard.
Can we
But
put
yes.
that on a cheat sheet by any chance?
Yes, you can put that on your cheat sheet if you want to. Yes. And those are called elementary row operations if you want the actual name for them.
Okay, thanks.
You're welcome. Other questions? Daniel, you had a hand.
So is the number of free variables the same as the number of basis vectors? I'm like, I should have reviewed my linear algebra more.
Yes, it is the number of basis vectors. It is also the geometric
Right.
multiplicity.
And
That's your other concept. Yes, from
Thanks.
linear algebra.
Okay.
Yes. So we've got algebraic and we've got geometric multiplicity. And if you don't know what those words mean and you're interested, take linear algebra, because now we've covered a lot of chapter 6, maybe something like that. You're doing a lot of chapter 6. Other questions? Yeah, Daniel.
Sorry, this is for the homework. On like the last one, so it's 5.4.
Yeah.
Section 5.4, number like 24. when we get the answer, so the book does a lot of things with the constants, which like I know I could have done to like simplify it, but could we also just say like C1
Yes.
times X and then C2 times quantity, whatever, and
Yes.
C3?
Yes,
Okay,
and this
thanks.
is partially why I put you in homework partners, so that you can check against each other as opposed to having to check against the book, which may or may not have the same answer as you do.
Yeah, okay,
Yeah.
sweet, thanks.
Cool. Okay, other questions? Tell me you're feeling decently okay about this. People who haven't had linear algebra, tell me you're feeling decently okay about this. Ish. All right. Tomorrow, very last thing, last new topic in the semester, we are going to deal with remember we said we had to do something different if our eigenvalue was defective. That's what we're going to deal with tomorrow. What's our something different? How do we get n linearly independent eigenvalues if we have a defective, n linearly independent eigenvectors if we have a defective eigenvalue? That's tomorrow. That's the very last new topic, and then we will wrap up the semester. Last call for any logistical questions. There's a bunch of stuff coming up, and I want to make sure you guys have everything clear as to what is due when and finals and all that jazz. Anything else? Other logistical questions?
What's your favorite Starbucks drink?
Caramel apple spice, because I don't drink coffee. Anything else? Okay, I'll send out homework, and then I'm going to go for a walk this afternoon because I have to get out of my condo with my winter hat and my winter coat and my gloves on. It's great. It's going to be great. Go outside, do something fun, and then come back and do your differential equations homework. I will see you guys tomorrow. Thank you. Have a good day. Bye.